show you this picture earlier? So this is a picture that made a lot of news in Norway at one point of time last year or so, where basically Norwegian ultra right-wing bozos were putting this on the Facebook, this picture, and say, oh my God, Norway is being taken over by burqa-clad Muslim women. We need to stop immigration, maybe build a fort or something. Okay? This is what was going on. Do you see burqa-clad Muslim women here? Some of you probably see. But then others of you might realize that these are just city bus seats. If you look at it at a certain angle, they look like burqa-clad Muslim women. So my point is, humans also make visually wrong classifications sometimes. But if you did look at it carefully and you thought this was a burqa-clad Muslim woman, the moment I said, hey, those are actually city bus seats, they say, yeah, that makes sense. Sorry, I made a mistake. Now I'm showing you, and you said in a school bus. Unless, of course, your brains are damaged already. You think this is an ostrich. But most people in Tempe still think this is a school bus. Then I say, hey, no, this is an ostrich. Do you think they will start realizing that now onwards this kind of a bus is an ostrich? They can't even tell the difference between this bus and this bus. They're the same bus as far as they're concerned. But they're completely different inputs as far as the neural network is concerned. Because there are, even if it's a 256 by 256 image, there are 65,000 inputs. And you're doing complex combinations of these inputs into higher order features and making decisions to training data to reduce the training error. And if there is a little noise in the training data, then you can show that there will never be any depth of adversarial examples. An adversarial example in this particular case is an example that not only drives the learner to make the wrong classification, it was clear that it's not in the distribution. This kind of carefully constructed school buses were not there in the distribution that I gave you. But that's like assuming that I'm going to build Death Star and only natural events will ever hit this Death Star, not Harrison Ford. But Harrison Ford knows exactly what the weak point is, and with 1.0 certainty he'll go hit that. If you put a machine learning system outside and people want to bring it down, they will generate adversarial examples and present it to them. And the fact that machine learning examples, algorithms, can do this kind of adversarial examples, not this kind that we kind of know that anybody can do, this kind where nobody in the loop would even think that the machine would have gotten mistaken by that. But the machine actually gives. In fact, one of the interesting things is, this was like, I think, its confidence that this is a school bus was very like 87%. That this is an ostrich is like more like 97%. It's more like an ostrich than it's a school bus. If any of this is confusing you, it should not. Because you set yourself this crazy task of taking 65,000 dimensional input, tuning 13 million parameters, or whatever, depending on how big your network is, to reduce the training error. At that point, all sorts of crazy things can happen. So one weird kind of overfitting that can be happening is really kind of, it's not actually overfitting, but it's these adversarial examples. So the machines are looking at the world, but not the way you are looking at them. And so, in fact, when the adversarial examples started coming onto the scene, so you tend to think that there is in some high-dimensional space, there is some nice, clean, convex regions. This is a chimp, this is a gibbon, this is raw, this is lemur, etc. But there is no reason for you to believe that is the way the way neural network is learning. In fact, it could very well be that it's learning something like this. Equally possible that it's learning something like this. That's one slither corresponds to chips. Another slither in this high-dimensional space corresponds to pandas. 99.9999999% of the space contains points that don't fall on any of these slithers. Then it's just basically seeing what is the nearest class. And now you start worrying about, oh my God, am I dependent on Tesla car taking me. I mean, because Musk is going to come out with it. So it all looked in the beginning when this came out, people used to think, this is just, basically people are trying to find some faults where there are no real faults. This will just go away. It's a mistake, small mistake, we'll just, a bug in the code will improve it. Ain't no bug in the code. This is par for the course, what we are doing right now. And so in fact, this is Jeff Hinton saying, I realize that this is a big problem, we don't know what to do. So in fact, his idea is capsule networks, which is some other thing that he came up with, might be slightly more robust. Nobody really knows. There could be advanced adversarial examples for capsule networks too. But really what is happening is this craziness of high-dimensional inputs. So in general, that particular guy, the theorem that he has says, adversarial examples for interpolated classifiers are asymptotically dense, assuming labels are not deterministic. Which means if there is noise in the training data, and the noise is not deterministic, then in order to fit to the training data exactly to have zero error, which anybody with full capacity can do, they would wind up opening themselves to large numbers, basically a dense set of adversarial examples in all these regions, approximately speaking. This is where we are with respect to neural networks. So what we'll do when we come back next class is actually do this one variant of neural networks called convnets, convolutional neural networks. Read up about them in the chapter and come and then we'll talk about them. Thank you.